had a middle class, and that's typically the people who have come to the U.S. and are very grateful.
You mentioned that you still have relatives there. Are you able to call them on the phone?
Yeah, we talk with them on the phone. It's you never know who's listening, of course, but it is possible.
Our guest is Umberto Fantova. His book is Fidel, Hollywood's Favorite Tyrant. Thank you for your time.
Thank you. Thank you.
And we're going to go across the street to Chapman Auditorium for our final live event today. This is a panel on science and inventors. The guests are Alan Lightman, Rebecca Goldstein, and David Levitt. Thanks for being with us this weekend at the Miami Book Fair International.
Come, don't be afraid. It's just an audience who likes writers. No. I want to begin by seconding Barbara. We have all had a great festival here. This is tremendous fun for all of us who leave our chilly and dismal climes to come here to Miami. And I know Dave Barry is going to be a tough act to precede us in this instant. If any of you heard the Rock Bottom Remainders last night, amazing rock band, to hear Scott Turow sing Mustang Sally is really something you don't want to miss. And I also want to thank Mitch Kaplan for putting together just an incredibly vivid, vibrant, festive event, and it's a joy to come down here. Finally, since I'm going on with such enthusiasm, I'm also grateful to be here in my fledgling role as a publisher. I started a company 3 years ago, and one of the ideas we had was to produce a series of books, which we call Great Discoveries, that would link great writers with scientific subjects. And this panel coheres. We have Rebecca Goldstein, the author of Incompleteness, on the life of the mathematician Kurt Gödel, and David Levitt, the author of The Man Who Knew Too Much, about Alan Turing. We have Alan Lightman, the professor of physics at MIT, who's now turned professor of writing at MIT, and whose book is this year is The Discoveries, Great Breakthroughs in 20th Century Science. The origins of this series, which we produce in collaboration with W.W. Norton, was to give a sense that science was accessible to the lay reader. And I thought of C.P. Snow's famous description of the two cultures, humanities and science, that were so remote from each other and so unable to communicate their knowledge. This is something that I was particularly aware of as a person in the humanities with a math SAT that will remain a blot on my entire life. It was so low. And I wanted to be able to cross this divide myself. When we started out, we weren't sure if it could actually be done. But to my amazement, it turned out that there were a large number of very well-known writers who were sufficiently adept at science to be able to write cogent, accessible, vivid narratives about science. And we began with David Foster Wallace, a book called On Infinity, Everything You Wanted to Know and More, and that was an accurate description. No, I'm the publisher. That was not an accurate description. And Barbara Goldsmith on Marie Curie, Madison Smart Bell on Lavoisier. It was very exciting to see these writers bring such a depth of knowledge to science. They are all three novelists. All three of our panelists are novelists of distinction. Rebecca is a professor of philosophy and has been writing novels. I remember very vividly her first novel, The Mind-Body Problem, about a young woman becoming aware of her sexuality, a young Orthodox woman at college. I remember vividly David's arrival on the scene, also about 20 years ago, with his first stories about family life. And Alan also became a novelist after establishing himself as a very distinguished physicist. I'll just go through the template here of their achievements, which are numerous, as you can imagine. Among Rebecca's other novels is Properties of Light, and if I may brag for a moment, Incompleteness was called an enthralling intellectual biography in The New Yorker, and compared to Davis Sobel's Longitude. She's also a member of the American Academy of Arts and Sciences, a MacArthur Fellow, and a recipient of the Whiting Award. David is the author of the novels The Lost Language of Cranes, Equal Affections, The Page Turner, and most recently, The Body of Jonah Boyd. And he just told me a few minutes ago that he's also started a literary magazine and has become an entrepreneur, and was talking to me more about distribution at Ingram's than about his new book. It's very impressive. What's the name of your magazine?
Subtropics.
Subtropics. And he's a recipient of fellowships from both the Guggenheim Foundation and the National Endowment for the Arts. Family Dancing, his first collection, published when he was just 23, was a finalist for both the National Book Critics Circle Award and the PEN/Faulkner Award. And the reason his magazine is called Subtropics is because he teaches creative writing at the University of Florida in Gainesville. Alan is the author of 4 novels, Einstein's Dreams, Good Benito, The Diagnosis, and most recently, Reunion, and numerous books on science, including Ancient Light, Great Ideas in Physics, Time for the Stars, and the book I mentioned just out now, The Discoveries. As I was thinking about these 3 panelists and what they have in common, I was struck by the fact that we often think of novels and novelists as engaged in some otherworldly occupation, writing dark stories about dark figures, which I suppose is true enough. And yet the precision in these books, their ability to deal with mathematical concepts and physics and scientific concepts, which they seem to have worked up and learned and mastered, not in any formal way, very impressive to me. But I also had an insight into the resemblance between the lives they write about and the lives of novelists. That is to say, and they will tell you about this, that the life of Alan Turing, the life of Gödel were as tragic in their own way as the lives of the novelists that we read about. And I think this congruency is really fascinating, something I hadn't thought of before. So I'm going to turn the proceedings over to them, and Alan will talk first for about 20 minutes, followed by Rebecca, and then David, and then we will have some discussion and take questions from the audience. So thank you very much, and welcome our panelists.
Thank you, Jim, for that wonderful introduction, and it's great for me to be here. I love Miami, and I thank all of you for coming. In one of the most remarkable narratives of scientific discovery, the German biologist Otto Loewi recalled how the idea came to him for testing the way that nerves communicate, and the idea arrived in a dream. And I want to read you Loewi's account of this dream. The night before Easter Sunday of 1921, I awoke, turned on the light, and jotted down a few notes on a slip of paper. Then I fell asleep again. It occurred to me at 6 o'clock in the morning that during the night I had written down something most important, but I was unable to decipher the scrawl. Haven't we all had that experience? The next night, at 3 a.m., the idea returned. It was the design of an experiment to determine whether or not the hypothesis of chemical transmission from one nerve to the next was true. I got up immediately, went to the laboratory, and performed a simple experiment on a frog heart according to the nocturnal design. Well, Einstein had his thought experiments, and Ernest Rutherford had his damn fool ideas, but very few scientists have had their great ideas in a dream. About 5 years ago, I decided that I want to explore the nature of discovery in science in the 20th century. Now that it's 2005, we can just start to grapple with a whole century of scientific thought. And I wanted to know how scientific discoveries happen. What is the mind of the scientist? How many discoveries are accidental versus intentional? Are the scientists aware of the significance of their work at the time? Are there common patterns of discovery? Is there a common creative process in science? How do styles of working and thinking vary from one science to the next and from one scientist to the next? How do the personalities of scientists compare? So I began badgering all of my friends at MIT and elsewhere, my colleagues in astronomy, physics, chemistry, biology, and asking them to nominate for me the greatest discoveries in their field in the 20th century. And I got about 100 nominations. And I decided I wanted to collect the original papers, because I think when you have the original paper, you can really hear the voice of the scientist speaking. And so I collected these papers, and some of them were hard to get. Some of them had been published in obscure journals. Some of them required translation into English. And I gathered them together. Here was the original discovery of special relativity. Here was the discovery of of the first hormone, another communication system for the body. Here was the discovery of the expansion of the universe. Here was the discovery of the nucleus of the atom. Here was the discovery of the structure of DNA, and so on. And I felt that these papers themselves were extremely important. There's a mythology in science that the original papers don't matter, that it's only the bottom line that matters, and I think that that mythology is wrong. So I felt that I had gathered together the great novels and symphonies of science, and I winnowed down this list of 100 nominations to about 24 papers and 24 discoveries. And in my book, I tell the human story of each of these 24 discoveries and try to compare the process in one against the process of another. And then I give the reader a guided tour through each of these original discovery papers. Otto Loewi and the discovery of how nerves communicate was one of my case studies. And in 1921, at the time of his dream, it was known that nerves form the principal communication system of the body. What was not known, it was also known that a signal goes down an individual nerve in the form of electricity. What was not known was how one nerve transmits its signal to another nerve or to an organ. In other words, how do nerves talk to the rest of the body? The leading theory for that was that process was also electrical, that each nerve generated a little electrical current which flowed to the next nerve. Loewi's middle-of-the-night experiment was not only simple, but it was elegant. And what he did was he took the hearts out of 2 frogs. He kept these hearts alive and beating by putting them in a fluid, and he removed all of the nerves from the second heart. He then inserted a little metal tube into each heart and filled it with a chemical called Ringer solution, which keeps an isolated organ alive. He then stimulated the vagus nerve of the first heart. Now, the vagus nerve is a nerve that slows down any organ. And he found, just as he expected, that the beating of that heart slowed down after he stimulated the vagus nerve. He then took the solution that was in the chemical that was in the first heart, and poured it into the tube leading into the second nerveless heart. And it also began slowing down. Then he did the same with the accelerator nerve of the first heart, stimulated it, and the accelerator nerve made it beat quicker and quicker. And then he poured the solution from the first heart into the second, and it also began beating more quickly. And this demonstrated without a doubt that there's some chemical that a stimulated nerve transmits to an organ to communicate its signal. This was the beginning of the science of neurotransmitters, such as adrenaline and acetylcholine, and it has had enormous impact on brain science. Well, I wanted to describe in a little more detail one of my favorite discoveries in the book. And this was a discovery by a very little-known woman astronomer named Henrietta Leavitt. How many people have heard of Henrietta Leavitt? Not many. Yes. Yes, Jim's company just recently published the first and only book about Henrietta Leavitt. Well, Henrietta Leavitt left very little behind. She wrote just a small number of letters to the director of the Harvard College Observatory where she worked. During her lifetime, she received no medals, no honors, no honorary degrees. There are just a few sentences about her in most astronomy books. And the problem that she worked on was how to determine distance in space. But she didn't know that that was the problem she was working on at the time. Let me just backtrack for 1 minute and say that a major problem in astronomy has always been, how do you determine the distance to the stars? Because when you look up into space, you just see like a two-dimensional photograph. You can't tell how far away those little points of light are. If stars all came in the same luminosity or wattage, then you would be able to tell, well, the brighter ones are closer and the dimmer ones are further away. But in fact, stars come in a range of wattages, and there's no reference point. So you can't tell how away the stars are. And without knowing how far away they are, you don't know anything about the universe. You don't know how big our galaxy is. You don't know whether there are other galaxies beyond our galaxy. You don't know really anything about the universe. Distance is key. And what Leavitt did is she found a way for computing the intrinsic luminosity, the wattage of a particular group of stars, variable stars that pulse on and off, unlike our sun, and change in brightness, getting dimmer and brighter and dimmer and brighter. And she found that there was a relationship between how the cycle time of one of these variable stars and its intrinsic wattage. And once you know such a relationship, then you can find one of these variable stars somewhere else in the cosmos. You can measure its cycle time. You can look up on her chart and therefore get its wattage. And then from knowing its wattage, you know how far away it is, just as you can tell how far a 50-watt bulb is by how bright it appears, or a 75-watt bulb. So she found a way of measuring the true wattages of stars and therefore giving astronomy its third dimension. Her discovery was used to measure the size of the galaxy, which is about 100,000 light years in diameter. And a light year is the distance that light travels in 1 year, going at 186,000 miles per second. Our sun is about 7 light minutes away. It takes about 7 minutes for light to get from our sun to Earth. The nearest star is about 5 light years away. And the galaxy, our galaxy, the Milky Way, is about 100,000 light years away. And using Leavitt's way to measure distance, an astronomer measured the size of our galaxy. Another astronomer in 19 24 measured that there are other galaxies outside of our galaxy. And in 1929, yet a third astronomer, well, actually it was the same astronomer as the second one, Edwin Hubble, measured that was able to conclude that our universe is expanding, that all the galaxies are moving away from each other, and there was a beginning in time about 15 billion years ago called the Big Bang, which has enormous meaning for not only science but theology, philosophy. And all of this was possible because of Henrietta Leavitt's work. She was born in 1868 in Massachusetts, the daughter of a very religious father, and she remained religious her entire life. She never married. She was called Miss Leavitt her entire life. And in 1895, she became an assistant at the Harvard College Observatory, where she worked with a bunch of other women in analyzing stars on photographic plates. Photography was just coming into use in astronomy around 1900, and suddenly you had a huge amount of data that you had to analyze, because each photographic plate could record the positions and brightnesses of maybe 1,000 stars. And so you needed cheap labor for all of this. And of course, where do you find cheap labor in 1900? You find it with women. This was actually one of the few jobs in science that women could get. And these women around 1900 were paid 30 cents an hour, which translates today into about $8 an hour. They were called computers. These women were called computers. Another thing about Henrietta Leavitt's story that I love is she eventually became deaf. And so she worked in this world of silence, analyzing these photographic plates of distant stars and distant space in this world of silence. I love that image. Her title the entire time that she worked for Edward C. Pickering at the Harvard College Observatory was just assistant, and she never wanted anything more than that. A few astronomers during her lifetime knew of the importance of her work, but she received no honors, as I mentioned, and she died young at age 52 of cancer. Before her death, she left all of her possessions to her mother, and I wanted to read to you a list of the possessions that she left to her mother. Bookcase and books, $5. Folding screen, $1. Rug, $40. Table, $5. Chair, $2. Desk, $5. Bedstead, $15. 2 mattresses, $10. 1 bond at $100 face value. 1 bond at $48.56. In 1925, 3 years after she had been dead, a member of the Swedish Academy of Sciences, which awards the Nobel Prize, wrote a letter to her saying that he would like to nominate her for the Nobel Prize. From my sample of 24 discoveries, I have created sort of a taxonomy of scientific discovery, which I've just published in the magazine New Scientist. And of course, it's risky business to try to categorize anything dealing with the creative process, because we don't really know exactly what goes on in the mind during creation. But I have attempted such a classification, and I wanted to read you a few of the categories. There are about half a dozen categories of discovery in all. First, there is the accident, in which the scientist discovers something that he or she was not looking for. Henrietta Leavitt's discovery was an example of that. Another was Alexander Fleming's discovery of penicillin. There is a rare category which I call principles first, used by Einstein, in which the scientist begins with some sweeping philosophical principle about the universe, really a way that the scientist wants the universe to work, and then derives the consequences of that postulate. And Einstein's work on relativity theory followed that pattern, where he started with a postulate about saying that there was no absolute motion, absolute rest in the universe. There's no such thing as absolute rest. You can only tell motion relative to another, another object. There is the timely clue in which the scientist receives a vital clue just at the right moment in time after they've been working very hard on a known problem. Barbara McClintock's discovery that genes can move around on chromosomes was an example of getting a very good clue just at the right time. Rosalind Franklin, Jim Francis, and Crick, Watson and Crick and Franklin also got a very good clue just at the right time in their discovery of the structure of DNA. There's a discovery by analogy when you use a previous scientific discovery to make you think of the right pattern for a new discovery. Hans Krebs, who discovered the citric acid cycle, used this method. This is a sequence of biochemical reactions that breaks food down into energy, and it follows a cyclic pattern where each chemical is regenerated, and you keep going around a loop regenerating the chemicals that came before. He had discovered a previous cycle in biochemistry and was thinking in terms of cycles. Many other scientists were working on this problem, but Krebs was the only one who was thinking in terms of cyclic processes, and so he was able to discover the missing steps to make this sequence of reactions a cycle. There is a discovery when new tools become available. Edwin Hubble, who discovered the expansion of the universe, had at his disposal and its exclusive disposal the largest telescope in the world, the 100-inch telescope on Mount Wilson. Other astronomers were working on the same problem, but none of them had this exquisite new tool. And finally, there's something I call the long haul, in which an astronomer not astronomer, but a scientist just works on a problem very hard over a long period of time and finally cracks it. And Max Perutzi's discovery of the structure of the hemoglobin molecule was an example of this. There is a common pattern that I found in many of the discoveries from the 20th century, and the pattern is something like this. First, you do hard work and you have a prepared mind. I don't know of any examples of great discoveries in the 20th century in science, even the ones that were accidental, in which the discovery was made by an untrained amateur. The prepared mind is extremely important. Next, you get stuck. Getting stuck is a very important part of the creative process. Somehow it seems to stimulate or catalyze the imagination. Getting stuck is a good thing, not a bad thing. And when we get stuck on problems, we should just be patient and know that that's stimulating our creative imagination. Then there's a shift in thinking or perspective, and finally, the discovery. And I think that this pattern of discovery is universal to the creative process. I've seen it happen with novelists, with actors, with musicians. It seems to be a very common pattern in many, but not all, creative discoveries. I wanted to end with just a couple of comments about the scientific personality. I think most non-scientists have a pretty good idea about what a scientist looks like and what a scientist is like, a stereotype. And those of us who are either scientists or have science friends know that that's really not true, that there's actually a wide range of scientific personalities. Some scientists are bold and brash and revolutionary, like Einstein or Watson or Rutherford. Other scientists are modest, shy, even quiet, like Krebs or Lisa Meitner, the nuclear physicist, or Henrietta Leavitt, who I mentioned. William Bayliss, who discovered the first hormone in 1902, was a man who was very cautious when he did science. He was careful. He loved the details, the fine print. And yet his collaborator, Ernest Starling, was brisk impatient, didn't have any patience for the details, just like the broad sweep of things. But what all of these men and women share, despite the differences in personality, is a passion to know, a sheer pleasure in solving problems, and an independence of mind. When the American biologist Barbara McClintock, when she looked back on her career later in life, she recalled that in high school science classes, quote, "I would solve some of the problems in ways that weren't the answers the instructor expected. It was a tremendous joy, the whole process of finding that answer, just pure joy." And when Lisa Meitner, the nuclear physicist who discovered nuclear fission, when she was a little girl, her grandmother told her that she should not sew on the Sabbath because it was bad luck and the heavens would come tumbling down. So the little girl decided to do an experiment at age 6. She took her sewing needle, touched it to her fabric, just touched it, waited a minute, looked up, nothing happened. Then she took a single stitch, she waited, looked up, nothing happened, and finally she was satisfied that her grandmother had been mistaken, and she went happily about her sewing. Thank you.
Hi, it's a great pleasure to be here, and I do just want to say one word thanking Jim Atlas for his great vision in seeing the narrative, the drama, the passion in science and making this series happen. I thought that I would tell you how it was that I chose Kurt Gödel as the subject of my book. When I first heard about the project and when I was first approached to contribute to it, it didn't take me very long to hit on Kurt Gödel as the man that I would want to write about. And there were basically 3 reasons that Gödel was the man that I chose. First of all, as Jim had mentioned in his introduction, I'm a novelist, but I'm also a professor of philosophy, and I was trained in philosophy. I got my doctorate in philosophy. I actually never had any intention of writing a novel until I wrote one. I'm the only novelist I've ever met who never had cherished this dream of becoming a novelist, but just had a novel in her and wrote it. And then wrote a few more. But I think of myself professionally as a philosopher. And the interesting thing about Kurt Gödel's work, his very famous result, which is called the incompleteness theorem, there are actually 2 related incompleteness theorems, and I'll tell you a little bit about what they say in a moment. But one of the very fascinating things about it is that this is a mathematical result with all of the precision of mathematics, with our proof, that's what we get in mathematics, and a beautiful proof, by the way, one that's in its general structure quite easy to grasp. The details are more complicated. But this is a mathematical proof with all the rigor and precision of mathematics that has something philosophical to tell us. It's important philosophically. Kurt Gödel himself considered himself more a philosopher than a mathematician. He was only interested in doing mathematics that had some sort of light to shed on philosophical issues. Mathematics is very puzzling to us as philosophers because it's our one area of knowledge where we can get certainty. There's not that wonderful story about Lisa Meitner and the sewing, that she had a theory here and she went and she did a little experiment and it wasn't it was falsified. Her grandmother's theory was falsified, and she could throw it away. Interestingly enough, in mathematics, experiments, falsifiability are irrelevant. We have proofs in mathematics. Once something is proved, and it's immune to revision. We philosophers call this a priori. It's somehow the proof of it is not at all dependent on experience. It's prior to experience. It's immune from empirical falsifiability. How do the likes of us, we offspring of random processes of evolution, how do we come by certainty? How do we have this kind of knowledge that is immune from revision, that it's just thinking and we can prove things? It's very, very mysterious. And one of the great mysteries is whether or not mathematicians, like scientists, are actually discovering something, whether they're discovering an aspect of reality or maybe a meta-reality, a reality beyond spatiotemporal reality that they're uncovering in their proofs. Or are we simply constructing systems and inferring the consequences? Is mathematics a higher form of chess? You make up your rules and then you see what follows. These are some of the questions that we ask about mathematics. They're not really mathematical questions. They're meta-mathematical. They're about mathematics. Kurt Gödel had very strong views about what the nature of mathematics was. He believed that it was discovery, that one was actually unveiling, one was actually discovering an external, objective, mathematical reality in one's proofs. We call this Platonism, mathematical Platonism, and Gödel was a very, very strong Platonist. People disagree very much over the philosophical implications of Gödel's theorems, but they were motivated by Gödel himself in trying to understand something of a philosophical nature. So as a philosopher, this is mathematics. That is extremely important and very, very interesting. It's an interface between mathematics and philosophy. Also, Gödel's theorems, even as, well, what are they? Maybe I should just state them first of all. There are two. The first incompleteness theorem says that in any formal system that is powerful enough, rich enough to express arithmetic, there will be a proposition which is stateable within that system, which is true, but can't be proved in that system. So the system is incomplete. It can never capture all of the true mathematical propositions, not even an arithmetic, which is the most elementary and simplest, the foundation of all other higher mathematics. So there's this incompleteness. This, to Gödel's Platonist mind, had seemed exactly right, that our systems are not creating these mathematical truths, that they're discovering them, but the mathematical truths are true independent of the systems. And the second incompleteness theorem is that one of the things that you can't prove within a system is the system's own consistency. This is known as the second incompleteness theorem. This is very devastating because an inconsistent system is completely worthless. You can prove anything in an inconsistent system because from a contradiction everything follows. So an inconsistent system is worthless, and while you're working in a system, you can't tell, you can't prove within that system that it's consistent. You have to go to a higher system in order to go back to prove the first system's consistency, but then how do you know that higher system is consistent? You know, you get a kind of infinite regress. It's not very comfortable. It's incomplete. And so this is fascinating, but what it actually tells us philosophically, is debated. We know what Gödel thought it told, but there's a lot of debate about this. But it's certainly of philosophical interest. It's philosophically rich. So that was very, very interesting to me. Also, another philosophical problem that has some relevance, perhaps, to Gödel's incompleteness theorem is the nature of the mind. If mathematical knowledge is somewhat mysterious, it casts a little mystery on the nature of the human mind as well, which has this mathematical knowledge. Even while Gödel was still alive in 1962, a philosopher named John Lucas had published an essay trying to use Gödel's incompleteness theorems to show that the mind can't be a computer, that we have mathematical knowledge that would exceed any programming, and that this was the implication of Gödel's incompleteness theorems. Quite recently, Roger Penrose wrote two mega-selling books, The Emperor's New Mind and Shadows of the Mind, trying to argue exactly this, that our minds are not digital computers, and that the basis of the argument is Gödel's incompleteness theorems. So there's something of real philosophical substance here in Gödel's incompleteness theorems, and so it was quite interesting to me. Gödel's incompleteness theorems, here's the sort of segue into the second point that made me very interested in Gödel. He's not as famous as his very good friend, Albert Einstein. They were very good friends. They had a legendary, famous friendship in Princeton. And so his incompleteness theorems are not as famous as Einstein's relativity theories, special and general, nor Heisenberg's uncertainty principle. But these three major ideas of the early 20th century, Gödel's incompleteness theorem, Einstein's uncertainty principle, and Heisenberg's uncertainty principle. Have I been saying Einstein the whole time? Heisenberg's uncertainty principle and Einstein's relativity are often linked together as part of a kind of postmodern attack on the notions of objectivity and rationality, that even in the hard sciences, there's relativism, there's, from relativity, there's uncertainty from Heisenberg, there's incompleteness from Gödel, that it goes along with a general skepticism about objective knowledge and rationalism in general. It was very, very interesting to me, probably the primary interest that I had in writing this book, that at least two of these three, Einstein and Gödel, who had this famous, very actually mysterious friendship because they were very different in their personalities. As Alan said, scientists don't have always the same personalities, and these were very different men, but they had this very, very fast relationship. These two, quite the contrary, did not believe that the implications of their very famous discoveries, was a rejection of objectivity and rationality, but quite the contrary. They interpreted their own discoveries as affirming the notion of objectivity, Gödel in mathematics and Einstein in relativity. This was part of Einstein's argument with quantum mechanics, or with a certain interpretation of quantum mechanics. I often would hear Gödel's incompleteness theorems sort of generally, vaguely associated with, we can't know anything, nothing is certain, nothing is objective, we make it all up. And it was ironic and paradoxical that he set out to prove exactly the opposite, and that's how he interpreted his mathematical results. The other reason I was so interested in Gödel is the man himself, the personality, the paradox not only that lies in the heart of the implications that have been drawn, the paradox that he actually assimilates into the proof itself, but the paradox of Gödel himself. He was an interesting man. He was quite neurotic, and he was. intensified and darkened into true paranoia. He died a very tragic death. He believed that he was being poisoned, and he stopped eating. And so he starved to death. So this was the man who was, he was at the Institute for Advanced Study when I was a student at Princeton. He was universally, in our very small little world, that is, designated as Aristotle's successor, the greatest logician since Aristotle. And he was the victim of such illogic in the more general, popular sense of the word, and such irrationality. Interestingly, it was a kind of rationality run amok. He believed there was a reason for everything. Everything was intelligible. One of the sayings that he had, I found it with his Nachlass, his literary remains there in the library of Firestone Library in Princeton, was Die Welt ist vernünftig. The world is intelligible, it's rational. And the irony and the paradox and the tragedy of this man who was able to see and go where no one had really gone before. He turned actually logic into a mathematically respectable field. His work had all sorts of interesting mathematical implications, and beyond mathematics, into metamathematics, into the philosophy of mind. It's extraordinary work of a logical sort, and yet he was, when it came to life, quite helpless, quite clueless, quite maddening, as a matter of fact. And this kind of character has always fascinated me. In fact, in my fiction, many of my books have dealt with characters who have this extraordinary genius, this ability to go where no man or woman has gone before, to be able to see with such lucidity, and yet who just bumble through life and are often, quite unhappy themselves, and certainly make people around them often quite unhappy, often their spouses. And so in my first novel, The Mind-Body Problem, there was a mathematical genius, and in my last novel, Properties of Light, there were 3 physicists who were of this sort, this extraordinary vision coupled with tragic unseeing. And when I actually think back, I had met Gödel when I was a graduate student, and I was at a party at the Institute, and there was just a very brief window when he was gregarious. He was a great recluse. After his one good friend, Einstein, died, he really didn't speak to anybody else. And I interviewed people at the Institute who had known him. No, he was completely isolated. He made people quite annoyed with his determination to always look for reasons for everything, and his insistence on all sorts of procedural requirements. He tried so hard to be logical that he was vastly illogical, and he made his colleagues quite upset, and they actually had very little to do with him. He was truly isolated. But for one very brief period, there was a period when he was gregarious for about 2 weeks, and he happened to be, I came to a party, and I was there, and then I read in one of the journals by Oscar Morgenstern, another person who had been at the Institute, that he recounts how Gödel surprised everybody, showed up at this party, and he was holding court among a group of admiring young logicians and mathematicians, and I was one of them. And all of us, of course, were way too intimidated by the appearance of the god to ask any of the questions. And there was one question in particular. I had wished I had asked him what he thought about this argument that had been published in 1962, trying to argue that our minds can't be computers, based on his own work. Anyway, I thought I would just read a little bit. This is after I do all the work of the proof, which, as I say, is a very, very beautiful proof. This is the other thing, is that one can get a sense of what it is that mathematicians mean when they talk about the beauty and the elegance of proofs. If you haven't experienced this for yourself, it can sound quite odd, but mathematicians aesthetics is very, very important to them. They have a deeply developed sense of beauty, and this proof it's a beauty. And it's quite accessible. Very few symbols are required. Anyway, this little section that I'm going to read is called Pink Flamingo. There it was, inconceivably, Kay Gödel, listed just like any other name in the bright orange Princeton Community phone book. It was a sweetly surreal moment. I had just arrived as a graduate student at Princeton, and just for the thrilling improbability of it, had looked up the name of the town's most dazzling mind, the reigning, if reclusive god at the fabled Institute for Advanced Study, a bucolic 3-minute stroll from where I was living. It seemed almost axiomatic to me in those days that the greatest mathematical mind, which happened at that moment in history to be identical with Kurt Gödel's mind, was necessarily identical with the greatest of all minds, Kay Gödel. It was like opening up the local phone book and finding B. Spinoza or I. Newton. The Princeton Community phone book had offered me the unbelievable largesse not only of a telephone number, but also of a street address for Gödel. Of course, once I had this information, there was nothing else for me to do but to hop on my bike and pedal my way over to see the house on 145 Linden Lane. It was a simple wooden affair, orthogonally situated in relation to the street, unlike all the other forward-facing houses. And this singularity seemed somehow just right. The neighborhood certainly wasn't Princeton's choicest. It was a hot September day, and the streets were treeless. And the street was treeless, depressingly exposed to the high noon sun. There wasn't a soul stirring around the Gödel house, but the visit did manage to deliver yet another surreal wallop. The sliver of a front yard was completely dominated by one of those pink plastic flamingos that stands poised on one skinny leg. I stared in disbelief at the bird. How could a man who had produced one of the most exquisite masterpieces of human thought have planted a pink flamingo on his front lawn? Of course, there was a Mrs. Gödel, a former cabaret dancer by popular report. She used to say she was a ballet dancer, but she wasn't. It was cabaret. Visions of Die Blaue Engel danced through my head, and I hastily attributed the lawn ornament to a Marlene Dietrich type, turned unlikely New Jersey housefrau. I was hardly the only Princeton denizen who was fascinated with the elusive celebrity of pure thought in our midst. I once found the philosopher Richard Rorty, very prominent philosopher, standing in a bit of a daze in Davidson's Food Market. He told me in hushed tones that he'd just seen Gödel in the frozen food aisle, pushing his food cart. I went tearing through the aisles, but the phantom of logic had vanished. What was he buying? I asked Rorty. For the rumor was that the man ate next to nothing. Rorty shook his head lugubriously and said he'd been too stunned to notice. But I guess we can assume it was something frozen. We all speculated about what our hero might be working on. There were strange rumors about a proof for God's existence, which turned out to be veridical. Gödel, like Leibniz, so I should mention, after Einstein died and Gödel really mixed with nobody, his closest friend was the philosopher, the 17th century philosopher Leibniz. He was quite obsessed with Leibniz, and like Leibniz, believed that everything was a priori. Everything can be deduced. There's a reason for everything. Therefore, the techniques of mathematics can unveil the whole of reality. Gödel, like Leibniz, believed that some version of the infamous ontological proof for God's existence was valid. This is an argument that tries to deduce the existence of God from the right definition of God. He mentioned to at least one colleague at the Institute, the philosopher Morton White, that there remained just one step to be clinched before his new version of the ontological argument for God's existence could be published. The tone of our fascination with Gödel wasn't consistently reverential. There was even a decided undercurrent of flippancy. We found it hilarious, for example, that the greatest logician since Aristotle deluded himself into believing that God's existence could be proved a priori, that he was perhaps contemplating the day when atheists would be brought round by a good stiff course in quantificational logic. The stories we swiped were gratifying in the way that stories of geniuses acting oddly are always gratifying. We cut our prodigies down to human size, domesticate their grandeur into cuddliness, with tales of their quotidian weirdness. Sometimes we miss seeing what is truly human within these prodigious talents. Yet one more irony that Gödel's story suggests. Thank you.
Well, I wish that I could claim that Miss Levitt was an ancestress of mine, but she's not. However, I will say that one thing I discovered in the course of researching my book on Alan Turing is that Alan Turing shared a birthday with me and also shares a birthday with Kinsey, the great sexologist. So conclude from that whatever you like. It makes sense that I should follow Rebecca and her wonderful book on Gödel by talking about Turing, because there are a lot of links between Turing's work and Gödel's. But before I get into that, I thought I would read a little bit from the beginning of the book. This is from a sort of prefatory first chapter, which will give you a little bit of a sense of who Alan Turing was and a little bit of a sense of his history. In Alexander McKendrick's 1951 Ealing comedy, The Man in the White Suit, Alec Guinness plays Sidney Stratton, a dithery, even childlike chemist who creates a fabric that will never wear out or get dirty. His invention is heralded as a great step forward until the owners of the textile mills at which he was employed, along with the members of the unions representing his fellow workers, realize that it will put them all out of business. Soon enough, these perennial antagonists join forces to trap Stratton and destroy his fabric, which he is wearing in the form of a white suit. They chase him down, corner him, and seem about to murder him, when at the very last moment the suit begins to disintegrate. Failure thus saves Stratton from the industry he threatens and saves the industry from obsolescence. It goes without saying that any parallels drawn between Sidney Stratton and Alan Turing, the English mathematician, inventor of the modern computer, and architect of the machine that broke the German Enigma code during World War II, must by necessity be inexact. For one thing, such a parallel demands that we view Stratton, especially as portrayed by the gay Guinness, as, at the very least, a proto-homosexual figure, while interpreting his hounding as a metaphor for the more generalized persecution of homosexuals in England before the 1967 decriminalization of acts of gross indecency between adult men. This is obviously a reading of The Man in the White Suit that not all of its admirers will accept and that more than a few will protest. To draw a parallel between Sidney Stratton and Alan Turing would also require us to ignore a crucial difference between the two scientists. While Stratton is hounded because of his discovery, Turing was hounded in spite of it. Far from the failure that is Stratton's white suit, Turing's machines, both hypothetical and real, not only initiated the age of the computer, but played a crucial role in the Allied victory over Germany in World War II. Why then labor the comparison? Only because, in my view, The Man in the White Suit has so much to tell us about the determining conditions of Alan Turing's short life: homosexuality, the scientific imagination, and England in the first half of the 20th century. Like Stratton, Turing was naive, absent-minded, and oblivious to the forces that threatened him. Like Stratton, he worked alone. Like Stratton, he was interested in welding the theoretical to the practical, approaching mathematics from a perspective that reflected the industrial ethos of the England in which he was raised. And finally, like Stratton, Turing was hounded out of the world by forces that viewed him as a danger, much as the eponymous hero of E.M. Forster's Morris fears that he will be hounded out of the world if his homosexuality is discovered. Dubbed as a security risk because of his heroic work during World War II, Turing was arrested and tried a year after the opening of The Man in the White Suit, and on charges of committing acts of gross indecency with another man. As an alternative to a prison sentence, he was forced to endure a humiliating course of estrogen injections intended to cure him. Finally, in 1954, he committed suicide by biting into an apple dipped in cyanide, an apparent nod to the poisoned apple in one of his favorite films, the Disney version of Snow White and the Seven Dwarfs, and one of which writers on Turing in subsequent years have made much of. An interesting coincidence that Rebecca and I were just discussing is that Snow White and the Seven Dwarfs was also one of Gödel's favorite films. I first learned about Turing really in the context of his role as a kind of martyr to the laws in England that criminalized homosexuality and under which Oscar Wilde was arrested and under which so many other men suffered. But that is one of only several identities. One of the things you learn when you work on the life of a man like Turing is that different people know him for different aspects of his work. He is known among historians of homosexuality and lesbian culture, gay male and lesbian culture in England, as a kind of a martyr. He is known among historians of World War II as a codebreaker, as really the single architect or the principal architect of the program by which the German Enigma code was broken. He is known among mathematicians as computer scientists as the inventor of what has come to be known as the Turing machine, but which he called the A machine, which was in some ways the theoretical prototype of the modern computer. And he is known among those who study artificial intelligence as the developer of the Turing test, although that was not his name for it, which is a test that in a sense tries to establish whether a machine can be distinguished from a human being. All of these discoveries and all of this work took place over the course of a life that was comparatively short and that was cut off by his suicide. I thought I would talk a little bit today about the discovery of the Turing machine and also about the Turing test. And this does relate to Gödel's work. When Gödel proved the incompleteness and the inconsistency of first-order mathematical systems, and I hope that the mathematicians in the audience will forgive me if my language is a little bit imprecise, he was responding to 2 of 3 proofs that the great German mathematician David Hilbert had called for in his effort to, in a sense, stabilize the mathematical landscape. Hilbert was very interested in the fundamental underpinnings of mathematics. He wanted the foundations of mathematics. And when he called for proofs of the consistency and completeness of mathematics, I think he took it for granted that the proofs would be positive. In fact, Gödel's proofs showed that mathematics was incomplete and inconsistent. But there was a third point that, that Hilbert was interested in, and that had to do with the idea of whether mathematics was decidable. And the way that he phrased the question was this. He said, does there exist an algorithm that decides the validity of any given first-order formula? What he was essentially asking was whether or not there was, he was asking for a proof, and as Rebecca pointed out so eloquently, mathematicians are in the business of proof, not disproof is easy, proof is difficult, proof is challenging, and it's in proof that the aesthetics of mathematics really come into play. Is there a proof, could a proof be given to show that any formula was either provable or unprovable? Decidable or undecidable? And this was known as the Entscheidungsproblem, or the decision problem. And when Turing began his career at Cambridge in the 1930s as a pure mathematician, and he was taking a course from Max Newman, who was a famous avatar of the field of topology, and Newman mentioned the as yet unproven Einscheidung's problem in a lecture. And when Hilbert's language was, Hilbert referred to the idea of a definite method for determining the decidability of a mathematical formula. Newman translated this into the idea of a mechanical process. This was Newman's term. And Turing, who was very, very literal-minded, heard the word mechanical, and he immediately started thinking of machines. Now, I was very, very glad to hear Alan earlier mentioning the fact that the word computer originally referred to the people, mostly women, who did computations. And that was very much the context in England as well as in America. And Miss Leavitt, my non-ancestress, was one of these computers. Turing was really the first person who took the idea of a computer as a person and turned it into the idea of the computer as a machine. Essentially, what he wanted to prove was that the decidability problem was insoluble. He wanted to prove, and this would be the third step in basically demolishing Hilbert's very idealistic program, he wanted to prove that there was no definite method, that there was no mechanical process by which the decidability of a given formula could be proven. And when he heard that word mechanical, he immediately started thinking of machines. And so he came up with this idea of a machine, a very, very simple machine that would correspond to a given algorithm, an algorithm being a method for solving a problem. And what he envisioned was sort of a small machine with an endless tape running through it. And on the tape, the machine could print two symbols. It could print a 1 or it could print a 0. And it could move the tape to the left, it could move the tape to the right, or the tape could stay still. And he started off with some very, very basic, simple machines that would perform algorithms as simple as adding 2 and 2 and getting 4. His first step in the proof was to show that these machines could exist, that for every algorithm there could be a Turing machine, even for the most complicated algorithms, even for such complicated algorithms as the Bessel functions and other very, very sophisticated algorithms. He proved that there was a corresponding machine, a machine that, with only these few capabilities, the ability to move the tape one direction or another, the ability to print a 1, the ability to print a 0, these machines could perform these algorithms and either generate a sequence of answers, every answer to the given algorithm. Say the algorithm is 1 plus x equals y. They would go through every single answer, or alternately they would simply provide the answer and then stop. He then expanded this idea to the idea of a universal machine. And the idea was if there was a machine corresponding to every algorithm, and you could actually number these machines and list them, could there be such a thing as a universal machine that could, in effect, interpret the instructions that would be given to each individual machine, and thereby, having interpreted the instructions, perform the function of that machine? And then, having developed the idea of the universal machine, he used this machine, this concept of the machine, to show that the decision problem was insoluble and that mathematics, in addition to being inconsistent and incomplete, was also undecidable. It seems to us now like a pretty revolutionary discovery, but at the time it was pretty much ignored. And that was in part because in those days mathematical logic was not in the best odor in the mathematical community. But it was also because Turing had been beaten to the punch. He'd been beaten to the punch by a Princeton mathematician named Alonzo Church, who had come to the same conclusion, but come to it in what I think we would all say now is a much less interesting way. Turing, I don't think, realized the implications of what he'd done. He had invented this hypothetical machine with no intention of ever building it. How, after all, could you build a machine that relied on an endless tape? There aren't really endless tapes in the world. It was part of a proof. But he had come across a revolutionary idea, which was that there could be a machine that could imitate the function of other machines and thereby be truly universal. And this was really the prototype of the modern computer. And Turing had come up with it really without realizing it. As he continued on in his career, he became increasingly interested in the idea of making the hypothetical Turing machine into a real machine. And as he moved forward in this, he encountered a number of roadblocks. One of the roadblocks was the Second World War, in which he was recruited to be part of the code-breaking effort at Bletchley Park. And this was both a positive and a negative. It was a negative because it took him away from it for a number of years from what was his principal interest in his principal work. But it was a positive in that it gave him some hands-on experience in machine building. He he really provided the theoretical underpinnings for the building of a machine called a bombe, B-O-M-B-E, which was the machine through the use of which the German Enigma code was broken. His idea was that if the code was generated by one machine, it would take another machine to break it. After World War II, he found himself confronted with, well, he'd been more or less, he hadn't exactly been beaten to the punch, but there already were computers in existence in America, principally a computer called the ENIAC, that were built on a very different philosophical foundation than his own. These were computers that required what he called screwdriver interference. They had to be, if you wanted to change what the computer did, you had to go in with a screwdriver and effectively rebuild it. Whereas here, his idea was a simple, even minimalist machine that could, in a sense, imitate any other machine. And in this regard, he was really coming up with a very early prototype of the modern idea of hardware and software. So he was ahead of his time in many, many ways, and at the same time, he was constantly being beaten to the punch and losing out on opportunities. The other problem that he had was he would be interested in something up to a point, and then once his ideas started to be realized, he would become distracted and become interested in something else. And in the later period of his life, he became very interested in the idea of artificial intelligence, and he came up with the idea of the Turing test, or the imitation game, he called it. And the way the imitation game worked was, essentially, you have in one room a human being, and in the other room a computer, and you ask them questions. And the idea is, on the basis of their answers, can you deduce which is the human being and which is the computer? Especially if the computer has been trained to behave in much the same way as a human being. His argument was that this would be a proof that computers could be said to think, that they could be said to exhibit intelligence, which was a very frightening idea at that time, principally because there was a lot of fear of the idea that if computers could actually think, they could take over the world and kill us all, and it would be a sort of a version of Samuel Butler's novel Erewhon, and all hell would break loose. And Turing was really convinced of this idea. And yet, behind the idea, there was a whole agenda, or a set of agenda, that had to do with his own experience as a homosexual man, or at least I would argue so. And a lot has been written about this, a lot of arguing back and forth, but I just want to give you a couple of quotes from the famous paper in which Turing proposed the idea of the Turing test, to give you a sense of how he was increasingly conceiving of computers as thinking, sentient beings, and also of the ways in which a lot of his own anxieties and concerns about his own homosexuality were starting to reveal themselves through his writing. And in a sense, the way in which, I would argue, his later work, especially his later papers, encoded a sort of a plea for tolerance and justice and equality towards all oppressed populations, including both human and machine, the oppressed population of machines and the oppressed population of gay men and women. This is a passage in which he's basically predicting the arguments that will be used against the idea of a machine being able to think. And one of these arguments he calls, there's a whole category of arguments that he calls arguments from various disabilities, which he defines as taking the form, quote, I grant that you can make machines do all the things you have mentioned, but you will never be able to make one do X. And he then offers a rather tongue-in-cheek selection of the various things that you will never be able to make a machine do. Be kind, resourceful, beautiful, friendly, have initiative, have a sense of humor, tell right from wrong, make mistakes, fall in love, enjoy strawberries and cream, make someone fall in love with it, learn from experience, use words properly, be the subject of its own thought, have as much diversity of behavior as a man, do something really new. And I should add here that another way in which Turing's argument, I think, encodes an argument for toleration of gay men and lesbians is that for him, behavior is identity. If a computer can persuade you that it's human, then it is human. Okay. As Turing notes, no support is usually offered for these statements, most of which are founded on principles of scientific induction. The works and customs of mankind do not seem to be very suitable material to which to apply scientific induction. A very large part of space-time must be investigated if reliable results are to be obtained. Otherwise, we may, as most English children do, decide that everybody speaks English and that it is silly to learn French. Turing then goes on, and I'll just read a little bit more, and then I'll stop so we can take some questions.
I think we're...
Are we out of time?
I can't
finish my argument. Okay. Well, thank you very much.
Not my fault. I'm sorry we didn't have time for questions. I had my own questions. I'm sorry I had to interrupt David. I was given a note. Welcome to Dave Barry. Thank you so much for attending.
To realize that I had no idea about these philosophical findings, and I want to thank you very much for that.
Thank you so much.